Hello! Today's lesson kicks off our new unit called Electrochemistry. As you can see from the name, electro having something to do with either electrons or electricity, and chemistry. And you're right, in this unit, chemical reactions are going to be harnessed to produce electricity, or electricity is needed in order for the chemical reaction to occur. But before we get to that aspect of our unit, we have to start off with the very basics. And that is learning about reduction-oxidation reactions. We'll go into more detail about these in our next lesson, but it's important for us to recognize that these exist. Earlier in this year, we learned that we categorize chemical reactions into 5 different categories: synthesis, decomposition, single replacement, double replacement, and combustion. For those of you who are listening carefully, I told you that this was the only time that we would be classifying it in these 5 ways. As soon as you get the bigger picture of chemistry and start to study it in more advanced ways, chemists actually categorize chemical reactions into 3 different groups. One of them is acid-base reactions, which we studied in depth in our acid-base and solution chemistry unit. Precipitation reactions, which we studied a lot throughout the course of the year. And finally, the 3rd category is this reduction-oxidation reactions. Now, looking at this word, reduction and oxidation, if we put them together, we get redox. And that is how so many chemists talk about these reduction-oxidation reactions. Redox. The reason why we take these 2 words, reduction and oxidation, and put them together to form one is because we can't have reduction without oxidation and vice versa. You can't have oxidation without reduction. So by taking the 2 words and putting them into one, it gives the impression that they do go hand in hand with each other. To help you with the bigger picture, in an oxidation reaction, the oxidation number of an element increases, and this occurs by losing electrons. In a reduction reaction, the oxidation number of an element decreases, and this is done when atoms gain electrons. We will be going into greater detail about these oxidation and reduction reactions in our next lesson. The whole purpose for us talking about them now in this first lesson is because our first lesson is going to focus on these oxidation numbers, because that's ultimately how these oxidation-reduction reactions are defined. What's happening to the oxidation number of an atom or an element? Is it going up or is it going down? So if you're taking a time now to write down the reduction-oxidation reactions definitions, that's fine. If not, you're waiting till next lesson, that's fine too. Our final bullet here gives us a little sentence saying Leo the lion says grr, and that's our Leo the lion, and when he roars it sounds like grr. The reason why Leo and grr are written in capitals is because they are acronyms. Leo stands for loses electrons oxidation, and grr, what the roar sounds like, stands for gains electrons. Reduction. Hopefully it's a cute little way to help you remember the difference between reduction and oxidation reactions and what's happening to the electrons. As you can see, oxidation is losing electrons, reduction is gaining electrons, and as we mentioned earlier, you can't have one without the other. You can't have a species gain electrons unless one is going to lose, and vice versa. You're not going to have one lose unless there's someone that's going to want to gain. So they definitely go hand in hand. And as I mentioned already, the purpose of this first lesson is to learn, how do I know what the oxidation number of an element is? So let's move on and get to those rules. Whoa, and there are a lot of them. We're pausing so that you have ample time to record what the rules for assigning oxidation numbers are. As you can see, they are listed in this fashion. However, it's not like you're progressing through the rules in a step-by-step format. These are all the rules at all the times. So let's go through them. Elements have an oxidation state of 0. Another way to rephrase that is elements have an oxidation number of 0. Oxidation number, elements. Let's keep going. All group 1 metals are positive 1. Oh. That kind of sounds like something we've done earlier this year. Bullet 3. All group 2 metals are positive 2. Oh, I kind of feel like group 1 metals, alkali metals, 1 valence electron, they lost it. That's why their charge was 1 plus. And alkaline earth metals, group 2, they had 2 valence electrons that they wanted to lose for their charge of 2 plus. For those of you remembering, you are on the right track. Oxidation numbers, what are they? They're not exactly a charge, but rather they're an apparent charge. The apparent charge of an atom in a compound or element. Now, the reason why we have that term apparent as part of the definition is because when you're looking at elements, right? Elements are electrically neutral. There are no electrons lost, no electrons gained, which explains this rule number 1. Elements have an oxidation state of 0. They have no charge. They're neutral. So their number is going to be 0. As for our compounds, well, technically, the only type of compound that has charged particles would be the ionic compounds, the salts, because we have this cation that lost an electron and this anion that gained an electron. Therefore, they are charged particles, and the charges attract to form the ionic bond. But what we don't have is the molecules, the covalent bond. They technically don't have a charge because those are all just neutral atoms that are sharing their valence electrons. They are not ions that are electrostatically attracted together. So that's where this adjective apparent comes in. Sometimes the oxidation number is the actual charge of the ionic compound, which brings us to these next 2 bulleted rules. Right? Group 1 are our alkali metals. Their charge was always written as 1 plus. To tell the difference between the actual charge and the oxidation number, the sign is placed funny. So in the charge, the sign comes after the number of electrons lost or gained. In an oxidation number, the sign comes first. So group 2 metals, alkaline earth metals, 2 valence electrons, when they form their cation, their charge, we wrote it as 2 plus. Notice that their oxidation number will be plus 2. So again, sometimes oxidation numbers are the charge. It's just that the sign comes first. And that will always be the case when we're dealing with compounds that are in ionic bonds. When you get to your molecules or your covalent bonds, that's where this apparent charge comes into play, and which brings us then to the rest of the rules. Let's work our way through them. All right, all group 7 elements are -1 in binary compounds with less electronegative elements. Well, group 7, those are our halogens. And we know that halogens have 7 valence electrons. So it makes sense that they're going to have an oxidation number of 1 minus, because again, their oxidation number would be -1 because their charge is 1 minus. They want to gain that electron, especially when they're bonded with less electronegative elements, right? The more electronegative element is the one that's going to do the gaining, hence why it will have the negative sign associated with it. Next rule. Oxygen is -2, except in peroxides where it's -1 and when it's with fluorine. That when it's with fluorine is our most electronegative element, so fluorine's going to be the one that winds up gaining the electrons and has a negative charge, so oxygen would wind up being positive. Hydrogen will always be +1 for its oxidation number, except when it's bonded with a metal.
It's 2:03.
Please excuse me, sorry. A metal hydride, hydrogen is acting as the anion. The metal, remember, is always going to want to lose its electrons. So when you have, for example, sodium hydride, the hydrogen will have an oxidation number of -1. The total value of the oxidation numbers in your compounds must equal 0. And that's true because our compounds are electrically neutral, and the number that represents neutrality is 0. And if you wanted to break it up in terms of polyatomic ions, the total value of your oxidation numbers in polyatomic ions must equal the ion's charge. If you haven't yet finished copying these rules, please pause the lecture and do so, because we'll move on and apply these rules to various examples. We'll work through 6 examples as part of our classwork, and then you'll have a chance to practice for homework. Again, the rules are not meant to be sequential. You don't take them one step at a time. You have to look at all the rules together and sort of deduce what your starting point is going to be. All right. My first example is KCl, potassium chloride. I know that this is a compound, so whatever number for potassium and whatever the number is for chlorine, when I add them up, they need to cancel each other out. Compounds are electrically neutral. Potassium is a metal. It's found in group 1. Chlorine is a halogen. It's in group 17. Both of those elements have rules associated with them. The rule for potassium says that all group 1 metals will have an oxidation number of +1. So I write +1 over the K. The rule about the halogens is that they're all -1. And just like we mentioned before, when I add +1 with a -1, that cancels out to be 0. So again, the oxidation numbers, how do you write your final answer? K with a +1 directly over it. It's not a charge, so you don't write it as a superscript, to the right of the letter. We're doing it directly on top of the element's symbol. The positive sign is coming first, and then the number. For chlorine, again, the oxidation number is going to go right over the symbol. We do the negative sign first, and then the value. So there are our answers. This is how we write it. Potassium has an oxidation number of +1. Chlorine has an oxidation number of -1. All right. Example number 2, potassium chloride, KClO3. This time I have 3 elements. I have K, Cl, and O 3 times. For some of you, it may be helpful to write them all out. What I do know is that this is a compound. So when I have these numbers, the number for K, Cl, and the 3 O's all together, those numbers are going to sum out to equal 0. Potassium is a group 1 metal. That has a rule. Their oxidation numbers will always be +1. In the previous example, we did chlorine. We were told that all of our halogens are -1 except if they're with a more electronegative atom. When you look at oxygen, it has a rule too. Oxygen will always be -2 unless it's a peroxide or if it's bonded with fluorine. So when given the choice in terms of what rule I'm going to follow, because the halogens have a little bit more wiggle room about what type of atom they're bonded with in terms of their electronegativity, whereas oxygen is more steadfast. It's always -2 unless it's a peroxide or it's with fluorine. I'm going to do my oxygens. Oxygens will always be -2. So that leaves me with, what is the oxidation number of chlorine? Perhaps some of you would like to solve for X. You're welcome to do so. Others may like to think of it more holistically. In other words, the 3 oxygens are going to contribute to a charge of -6. I know that my charges eventually need to cancel out and be electrically neutral. So that means the potassium and the chlorine must somehow contribute towards a +6 to cancel out the -6 from the oxygen. Well, potassium is accounting for +1 of the +6. What must the chlorine account for? Yep, you've got it. Chlorine is going to be +5. Our answer then is written as such. Potassium with the +1 on top of it, chlorine with a +5 on top of it, and oxygen with a -2 written on top of its symbol. Let's talk a little bit more about what this means. KClO3. That's going to be an ionic compound where you have the potassium and the chlorate polyatomic ion coming together. But the chlorine and the oxygen are going to be held together with covalent bonds. This apparent charge is showing you that oxygen is more electronegative, so it's going to have access to more of the electrons more of the time, and the chlorine is ultimately like losing its electrons. It's not a complete transfer though. This is what humans are trying to do in order to explain nature. We came up with this bookkeeping method that we call oxidation numbers. These are not actual charges, they are apparent charges. And by looking at these apparent charges, it's going to be easy for us to determine which atom is being oxidized and which atom is being reduced in our redox reactions. If I could just bring your attention to one more part of this compound, one of the rules that you wrote down said that you could also look at the polyatomic ion. In other words, ClO3 has a 1- charge. In other words, the chlorine and 3 oxygens, their oxidation numbers are going to have to sum up to be a -1. Again, we know the oxygens will be all -2. What must the chlorine have to be? Again, a +5. So when you go back to those rules, the way I've done the first 2 problems is I've emphasized the fact that the value of the oxidation numbers of the compounds must equal 0. For those of you who would like to take a compound and break it apart and only focus on the polyatomic ion, that is a fine way to do it too. As you can see, you'll come up with the same answer. But just remember that the polyatomic ion won't sum up to be 0. It's going to sum up to be whatever the charge of the ion is. Notice that both methods still get us to the same answer. So both ways are fine. They're just written as 2 separate rules. Which brings us to our third example, a polyatomic ion. Let's see this in action. BRO with a -1 charge. What does that mean? Well, it's not a neutral compound. Whatever the number for bromine is, whatever the number for oxygen is, when I add them together, they're going to have to sum up to be this charge of -1. So how am I going to decide which rule to follow? Well, bromine and oxygen are both nonmetals. Bromine is a halogen. Oxygen is not. Which one has the steadfast rule? You're right, good memory, oxygen. We know that oxygen is always going to have an oxidation number of -2, unless it's a peroxide or it's with fluorine. What then does the oxidation number of bromine have to be? Because that one doesn't have a steadfast rule. And remember, it has to add up to be a -1. So for those of you who said +2, you're not quite there. It's going to be +1. +2 would cancel out the -2, but I don't want both of them to cancel. I only want one of the two to cancel. My overall has to be a charge of -1. So writing our answers, bromine +1 is its oxidation number. Oxygen is -2. Now some of you may be getting the hang of this. Congratulations. Others not so much. All right. We still have 3 more practice problems we'll work our way through. All right. Iron 2 phosphate. Seems to get a little complicated because we've got subscripts as well as the parentheses, but just take it a step at a time. What does this mean? It means we have 3 irons, and it means that I have 2 phosphates. All of those atoms, when we take their oxidation numbers and add them up, they're all going to sum to equal 0. Another way I could figure it out is by focusing just on the polyatomic ion, phosphate. So one of those POOOOs are going to have to sum up to be the number of -3. Is there a right or wrong way to start? Not so much. You should eventually get to the same answer. But when I look at this, iron is a metal, but it's not group 1 and it's not group 2. There's no steadfast rule for what iron's going to be for its oxidation number. So I'm not going to be able to start there. There's no rule that involves phosphorus. Can't start there. So the only atom I'm able to start with is the oxygen. I know that each of these oxygens will be an oxidation number of -2. And here's where I'm going to have to implement the polyatomic ion rule. Phosphate, if you forgot, haven't memorized it yet, is PO4 3-. Well, if I know that those 4 oxygens are giving me -8, right? -2, -2, -2, -2. That gives me -8. What does the phosphorus have to give me so that X and -8 will sum up to be this -3? That's right, +5. Well, since I need 2 phosphates, the other P must also be +5. Now, how can I figure out the number for the irons? Well, I don't know what they are, but I know that they're all going to be the same number, right? See how each of these oxygens are exactly the same number? We wrote them each a total of 8 times. Same thing with the P's. There are 2 P's and they're the same exact number. So whatever the number is for iron, it's going to be the same for all 3 iron atoms. So cleaning this up a little, we've got +10 from the 2 P's, and I've got -16 from the oxygens, and then there are these 3 X's, right? And I know that all of that has to add up to equal 0. And my slash here is not meant to be a division sign. It was just meant to be positive versus negative. So I'm sorry for confusing you. But here's what it ultimately looks like. 3x, because I don't know what irons are, plus the 2 5s from phosphorus, plus the 8 -2s from oxygen. That's all going to add up to be 0. So we've got 3x plus a -6 equals 0. 3x is equal to 6. X is equal to 2. Each of these irons has to have an oxidation number of +2 in order for this compound as a whole to be electrically neutral. Now, maybe some of you remember what I've been saying before. Oxidation numbers are an apparent charge. When you've got an ionic compound, it's going to be the same number as the actual charge. So if you remembered that this is an ionic compound, and I need 2 of the phosphates to help balance out the number of ions that there are, right? Remember we uncrisscrossed? This number 2 is really telling you the charge of your iron. So some of you probably recognized what the oxidation number of the iron was from the beginning. I just wanted to continue to go through the steps or the rules so that you can see that you can still solve it systematically in that fashion as well. All right, example number 5. HSO3 with a -1 charge collectively. In other words, the number for the H, the S, and the 3 O's are all going to equal this -1. Looking at the rules, where will we start? Well, maybe some of you are going to oxygen. Oh, wait, I didn't write out my answer final. Oh, so sorry. Iron is +2. Phosphorus is +5. Oxygen, -2. That's your answer. So sorry that I didn't finish out that problem. Okay, now problem number 5. So again, the 1H, the 1S, and the 3 O's, they're all together. Their oxidation numbers are going to add up to be -1. So maybe you want to start with oxygen. We've been practicing so much. It's always -2 unless it's a peroxide or it's with fluorine. Neither a peroxide nor fluorine are appropriate in this formula, so oxygen's -2. Between hydrogen and sulfur, hydrogen has a rule. Hydrogen will always be +1 unless it's bonded with a metal, and there are no metals in this compound. So that brings us to sulfur. There's no rule for sulfur, so I need to solve for it. Well, the -2, -2, -2 equal -6. That means the sulfur and the hydrogen have to start to cancel it out. They together will be positive, but I don't want it to be +6. I want it to sum up to be +5. Because remember, the contribution of all these atoms together needs to give me a -1 charge. So if hydrogen is taking up 1 of the 5 positive charges, what must the sulfur take up? You got it, +4. Writing our final answers, the oxidation number for hydrogen is +1. The oxidation number for sulfur is +4. And the oxidation number for oxygen is -2. The answers are always what numbers are you writing over each element's symbols. And our last example together, Cr2O3. Well, it's a compound, so I know that the numbers for the 2 CRs and the 3 O's are going to have to cancel out to be electrically neutral. Oxygen has a rule. Its oxidation number will always be -2 unless it's in a peroxide or if it's bonded with fluorine. There is no rule for chromium. It's something that I'm going to have to solve for. Again, the way I go about solving for it is I know that these are going to need to cancel out. The 3 oxygens will contribute to a charge of -6. The 2 chromiums have to cancel it out. So together they're going to give me a total charge of +6. There are 2 chromium atoms that contribute to this +6. So what value goes with each of them? Yep, +3. So cleaning this up, the oxidation number of chromium is +3. The oxidation number of oxygen is -2. Here's where we'll stop with today's lesson so that you now have a chance to practice assigning oxidation numbers. Please access the homework assignment that's in our Google Classroom, and I look forward to seeing your results.